mentioned, we're a training company, and you can book a meeting with myself if you want to discuss your company's learning and development requirements or your individual training requirements. The rules for the webinar, just to keep it orderly and manage it, that we will automatically mute the participants. Questions will be through the chat function. Happy to take them during the webinar. I'll answer what I can and throw over to Peter at the end of the session if I can't answer the questions. And as mentioned, if we don't answer all the questions live, we'll follow up via email. And the webinar, as we just mentioned, is being recorded. And if you do have any questions after the webinar or want more information on the webinars we've been doing or training, just contact us at training@asandaengineering.com. Okay, oops. So I'll just turn that off and I'll hand over to Peter. So you can introduce yourself, Peter, and when you're ready, get your slides up and go through the webinar. So you're on, yeah. You're on mute, Peter. Sorry.
Good morning and good afternoon, ladies and gentlemen, all around the world. We have 350 registered, so lots of different time zones here. I hope you're able to fit in with this. My background is an engineer, originally with BP, more latterly managing independent oil companies where I was responsible for environmental aspects of the work. And I've been showing a keen interest in what's happening with the energy sector. I want to share with you what this climate change agenda is likely to do to the energy supply and forecast and what the growth looks like in different sectors. And it'll end up with a short summary on how this affects you as your career goes and also as your company's strategy works. And towards the end of the slides, we'll wrap that up. I'd like to just leave you with a message before we get started here, which is that there's a huge growth industry coming up for anybody who wants to transfer to the transition zone energy sector and renewables in particular. And also good news, the energy sector in the oil and gas area is going to be very, very healthy the next few years with shortages coming up and lots of need for investment and expertise to stave off an energy crisis, such as we're beginning to see around the world now, thanks to the Ukraine war. Okay, thank you, ladies and gentlemen. You can see my email address at the bottom there. If you've got any questions at the end of the session and you can't get it addressed during the session, feel free to email me and I'll try and get back to you. I won't go through the list of contents here. Briefly, what it is a summary of the climate change situation and a comparison of different energy types, including renewable like hydrogen and wind power, solar power, and geothermal. Then an outlook for the UK, what's happening here, and then business and career opportunities towards the end. So I'll start off by looking back at what's caused climate change in the past and how that influences the future. Climate change has been happening since the beginning of time, and I've categorized it here into major, medium, minor, and short term. The major ones are 1 to 10 billion years since the beginning of the formation of the Earth. Not of concern to us here. Medium, 1 million to 1 billion years. Minor is more relevant to us, 1,000 years to 1 million years. It's relevant because we're in a period of global warming on a natural basis here, caused by the Milankovitch oscillation, which is an oscillation in the orbit of the Earth around the Sun, and it repeats roughly every 100,000 years. And because of that, we're now in a warming trend which is going on for 18,000 years since the end of the last ice age. Short term is what we're interested in here. Things that affect short-term climate are things like short-term oscillations, El Nino and Gulf Stream, for example, volcanic eruptions, which is probably related to plate tectonic activity, and that you quite often get quite a few happening at the same time in different parts of the world. Much more importantly, solar output anomalies every 11 years and also every 22 years. Small meteoric impacts, minor change really, but a big meteor could have a lot of effect. And then the one we're really interested in here, which is anthropogenic. So since the hello, I can't talk. So the era, 1850 was the start of the industrial era. 1900, 1950, 2000, I've shown the different transitions from different kinds of energy through these phases. Transportation used to be mostly wind for sailing, sometimes rowing, horses for transportation across land. And then we get into the coal era, and mainly in 1900 or so. And then we shift into petroleum in 1950s. This is the major supplier of energy for transportation. And that's still the case today. Heating, again, you can see that trend from wood and coal through oil and gas. Light used to be supplied mainly by burning wood or tar, where there was tar available, and sometimes candles. More recently, whale oil for lighting oil. The whales were saved by the petroleum industry because it replaced whale oil with petroleum oil, which was more abundant, cheaper, and it saved the whales in the process. Industry used to be powered mainly by hydro and then by coal. And then it shifted into oil and gas and electricity. Electricity basically didn't exist in 1850. And again, you see the transition from coal into different kinds of energy supply today, which is hydro, coal, nuclear, gas, and so on. The bottom of this picture is a little set of pictures to kind of summarize all of that. So how have recent greenhouse gas effects had on climate? How do we get to where we are? So here's a graph of the temperature against time since 800 AD. And the white line is the plot of the temperature. The red line is the kind of band within which it works. And then on the top there, you can see solar sunspot numbers. Basically, high sunspot numbers means warm climate. And you can see there's a correlation here where we have high sunspot numbers and relatively high temperatures. And low sunspot numbers during this period here, which is called the Little Ice Age. There's the sunspot number there. So there appears to be a correlation between sunspot numbers and climate. Another graph here showing temperature history. This has influenced politics quite a bit because there have been two noticeable drops in average surface temperature. One on the left-hand side up to about 1900, during which time GHG greenhouse gases were going up in number, so the line should have been going the other way. Then we get into a rapid warming. And then starting around 1940 through to 1970, you see a global cooling. During this time, the media was fixated with the risk of a future ice age. So that's an interesting phase in the history of climate. We can't tell, of course, if this is going to happen again, and it probably won't reverse the long-term trend, which is warming temperatures. Here's an example of how the carbon dioxide levels correlate with global temperatures, going back to about 1880 or so. The CO2 concentrations in the black line there And then the temperature is in blue if it's less than 57.5 degrees Fahrenheit, and red if it's above that. So as is well known, we're in a warming trend right now. And believe it or not, the CO2 levels follow that curve. So it's reasonable to assume that the CO2 levels are causing the warming trend. But if you go back,
Sorry, Peter, you've gone on mute somehow, maybe by accident.
can you hear me now?
Yes, yeah, that's good.
Okay, thanks, Anastasia, for letting me know. I didn't see that.
That's okay.
So if you look at before 1970s or so, there was not a good correlation. CO2 was going up and global temperatures were still quite low. So again, questions when this information came out as to what the impact of CO2 really was. Now this is very interesting, this plot here. This plots solar irradiance in yellow. This is a NASA plot here, so quite reliable story. And the global surface temperatures in red. And as you can see, quite a good correlation up till about 1960 or so. The red goes up, that's the solar radiation, and shortly thereafter, or simultaneously, the yellow goes up, which is the surface temperature. Then, sorry, it's the other way. The surface temperature is yellow, and the surface temperature is red, and the solar irradiance is yellow. Then, interestingly enough, after 1960, they go opposite directions. The solar irradiance goes down. So if it was the main cause, you'd expect temperature to go down. It's not. It's been going up. So that, in a nutshell, explains why there's a lot of interest in the global climate situation, because it appears to be today to be caused mainly by CO2 levels. This translates also to sea level rises, and here's a plot which shows sea level rise since 1995 or so, 1990 or so. And this is from satellite data. It's about 3.3 millimeters per year. Another way of looking at it is they're taking surface measurements, which have been going back longer in time and are more reliable. And that's a little lower rate of rise, 1.75 millimeters per year. And it's fairly steady. It's not going up dramatically. It's steady rise, but it's not huge. At this rate, if we have no reduction in GHG emissions, sea level rise will be about 14 centimeters from today until 2100. So that's not a lot. It's about 6 inches or so. Now I'm going to show how this translates into oil, gas, and renewables outlook. There's a plot from BP showing that in the green you've got I can't see my screen's covered over here, but the green from memory is oil, and that sort of steadies out around 2040 and stops growing, but it doesn't drop like a lot of people have been saying, because there's still a strong need for oil and gas alongside the renewables. Gas in red, showing that growing steadily, partly because it's the transition fuel into low GHG energy sources. And then nuclear and renewables and hydro. Renewables are the fastest growth here, from a small level at the moment up to a much bigger, like 10 times higher level over the next 20 years or so. What are the main sources of CO2 emissions, and how can emissions be reduced, and how can energy efficiency be improved? This is a theme throughout these slides. Energy efficiency is the main, most effective way of solving the GHG problems, because other sources of energy all have their own problems. And energy efficiency has no problems at all. It's you can double energy efficiency in vehicles and in buildings. So that's the key one there. This slide shows the comparison of different countries' contribution to CO2 emissions. China is the biggest in the red there, USA second largest, then EU, Russia, Japan, and then the rest in the other category. Here's an interesting one. This is from Global CSS Institute. If you look at where we are today in emissions from CO2, it's currently 34 gigatons per year. And that's where we start this plot, looking forwards. If we do nothing, and the GHG levels stay as they are, there'll be a slight ongoing rise shown to 2050, which is called stated policies scenario. If we are to achieve the IPCC objectives in these various COP21s, COP26s, and so on, which are looking ahead, typically 30 years to 2050 and 80 years to 2010, but till 2100. How do we get to from the red line down to the green line? The contributions there are shown in the graph. They are basically efficiency gains 37%, renewables 32%, fuel switching 8%, CCUS 9%, and others 14%. On assessors, are you able to take off the people that are accepted into the call, because they're interfering with the screen a bit?
Sorry, say that again, Peter.
I've got on the right-hand side of my screen, I've got some participants who've been blocked, by microphones being blocked, but they're on my screen, and it makes me difficult to see the screen. It may also be interfering with the screen you see as well.
No, I don't seem to have that problem.
Let me see if I can.
I mean, we can see your presentation clearly. There's no issue with that.
Yeah, it must be something to do with my computer then. Hang on one second. Okay, I'll carry on then.
Yep, okay.
So ways of reducing emissions. First of all, reduce the amount of energy we use what we have more efficiently. Efficiency has improved globally since 1970, with a 60% reduction in energy consumption per unit of GDP. However, GDP has been going up, and human population has been going up, so there's pressure all the time for GHGs to increase. But there are some quick wins here. One is efficiency gains. For instance, in the US, roughly half of US energy consumption could be saved by more efficient energy use. It takes a few years. One is market driven, of course, where you have high oil prices and high gas prices now, then it encourages energy efficiency. So that will happen anyway as oil and gas prices go up. We can reduce emissions for a given level of energy, switching to gas, wind, solar, and reducing the use of coal and oil, for example. And we can increase carbon sinks. That can be achieved by more rainforests, both tropical and in the high latitudes. You know, the largest forests over Canada and Russia are big CO2 sinks. We can develop more agriculture. Plants and crops absorb carbon dioxide. And then we can sequester CO2 by storing in depleted oil and gas reservoirs or aquifers, which is called CCUS. Moving on, slide 20 here, the bottom right of the slide is GC20. There is no ideal source of energy. They all have their problems. So the best solution is to improve energy efficiency, which has no environmental complications. One of the mechanisms that has been touted quite a bit in the Western countries, the developed countries, is to set up emission schemes. But at the moment, only 15% of CO2 is traded. So the other 85% is untraded. A big chunk of those traded emissions are in the EU. And that could be the future for putting pressure on big polluters to cut back on CO2 emissions. Another example is vehicle mileage efficiency. That can be dropped in half through more efficient fuel usage, different types of engines, better aerodynamics. Improving building insulation, again, can be reduced by half, mainly through better insulation. And then a new one here, which is becoming very popular, is heat pumps for heating, which gets more heat per unit of energy than conventional systems. And using low carbon fuels or electricity. Low carbon fuel example is natural gas, which is low carbon compared with coal and with petroleum oil. Another big one here is methane emissions. Methane emissions are big around the world, and they contribute to a big chunk of global warming, the GHG emissions. They can be reduced. They are much more harmful than flaring. So wherever you have emissions, they need to be converted into heat through combustion, and then at least the emissions will be reduced. And also leaks can be stopped by going through production facilities in detail and stopping leaks wherever they can be found. Methane is responsible for 25% of global warming due to GHGs. 60% of methane emissions are man-made, the rest is from natural seeps, like wetlands, volcanoes, and so on. Of the man-made portion of methane emissions, about 1/2 is from fossil fuels and 1/2 is from agriculture. So two things here that are kind of standing out as obvious conclusions. One is that whatever we do to reduce temperature, the growth cannot be stopped because it's a natural process that's been going on for 18,000 years. But the future growth can be curtailed, but it cannot be stopped completely. There'll always be natural temperature rises caused by the Milankovitch orbital variations. And also, if we cut out man-made GHGs, you can't stop the natural GHGs, and those will continue in the background, going up all the time. Options for oil and gas operations to reduce methane emissions. First of all, eliminate leakage from pipelines, especially LNG, which boils off large volumes. When it's shipped, it emits a lot of methane through the boil-off process. Eliminate flaring and venting from process facilities such as oil tanks. If there's a choice, it should be flared rather than vented. Improve leak detection using ultrasonic, optical gas imaging, infrared gas detection, and other processes. Detection and measurement for satellites, aircraft, and drones. And then stopping procedures which release methane. Now here's a summary of what's happening with carbon capture, utilization, and storage, commonly known as CCUS. Here's the process. You start with oil and gas consumption, which is combined with air to make the CO2. And the types of plants we have doing this are power stations, cement plants, ironworks, and refineries. Those are the biggest four categories. They produce flue gas, which is a mixture of carbon dioxide and nitrogen. It goes to a carbon capture plant, which is typically an amine plant, although there are other plant designs in research stage. The amine plant captures the carbon dioxide and releases the nitrogen back into the atmosphere. And then the carbon dioxide is either utilized for cement plants and so on, or it can be shipped in pressurized cold liquid form, or it can be piped. And it typically goes to underground storage, of which there are two types. There's depleted oil and gas reservoirs, which is the preferred one because it's already a proven leak-proof system. And the other type is called saline aquifers, but they're less proven because they're not proven not to leak. So if you put CO2 into those, they could leak out through incomplete seals. Looking at CCUS, there are 19 projects in operation worldwide, capturing 35 million tons of CO2 annually. Further 32 are under development. This will bring the capacity to 96 million tons of CO2 per year. However, this is very small compared with current CO2 emissions, which are 32 gigatons per year. So the IEA Sustainable Development Plan calls for CCS to contribute 7% of GHG emission reductions. If the plan is implemented and a total of this amount is captured, it's still 1/25 of the amount that is currently in operation. So there are 25 times higher emissions than current CCUS projects in operation and under development. Carbon capture costs average at the moment, or the projection is that there'll be $60 per ton of CO2. Capture costs are 60% of the total. Transportation of CO2 is 18%, storage 22%. So the capture cost is the biggest component. And in rough approximation, the cost of capturing CO2 and injecting it and storing it is about the same as the cost of producing natural gas, because the process is the same as the natural gas process, but in reverse. So you still need wells, storage reservoirs, pipelines, and processing plants. The EOR schemes are generally economic, especially in the USA, because they can do extra oil production and sometimes gas production as well. And sometimes they have in the past had government subsidies to encourage this. CO2 can be single phase or liquid at typical storage conditions, improving storage volumes. So that's quite a plus, that one. There are 3 projects getting quite a lot of attention in Europe. One's called the Net Zero Teesside project, formerly called the Clean Gas Project in Northeast UK. It's built in an industrial area. That's where it's planned to be constructed and operated. Should be operational in the latter part of this decade. Partners are BP, Eni, Equinor, Shell, and Total, so some big players there. And they will capture about 10 million tons of CO2 annually from the Teesside industry, which is 5% of UK emissions, and inject into the southern North Sea where there are depleted gas fields. Another project, again funded by the majors Shell, Total, and Equinor, called the Northern Lights in Norway, is to capture CO2 from multiple areas, combine them, and then inject in the Jurassic near the Troll field, starting fairly soon, within the next 2-3 years. Well, that's fairly optimistic now. Then another one called the Portas project in Holland, which captures 10 million cubic feet, 10 million tons per year of CO2 in Holland, pipe it offshore and store it in depleted gas fields. So, what are the advantages and disadvantages of different energy types? I'm sure you've been looking at the growth of solar and wind and geothermal as examples, and I'll try and summarize what's happening here. First of all, here is a comparison of different energy sources: coal, oil, natural gas, nuclear, geothermal, hydroelectric, biofuels, bioenergy, wind, and solar. Points in favor and in the green column, points against and under the red column, and some other comments in blue there. Very briefly, coal is inexpensive but very polluting, especially when it comes to GHGs. Oil is almost as inexpensive as coal. Sometimes there's price hikes like now. Medium carbon intensity and will be needed in the future for a number of different applications which cannot be easily filled by renewables. Natural gas is the best of the fossil fuels with low carbon intensity, competitive price, the chance to build further with international trade with LNG, which will also get a boost from the Ukraine war situation, make up for the shortfall caused by the Russian gas supply situation. Natural gas is difficult to transport long distance, which is why you need LNG for long distance transmission. Shale oil has been, and shale gas, gas has been a big growth area in the US in particular. It needs high oil prices to make it economic, so it's coming back into action with the current high oil prices, although they went for a lull for about 5 years because of low oil prices. Nuclear really doesn't have much of a future because of safety issues, and that's been amplified somewhat by the Ukraine war situation, where there was a military confrontation next to Chernobyl. And that raised questions about the safety of nuclear during wars and so on, or during terrorist operations. So unlikely to get much traction in the future. Also very high capex in the billions of dollars, and usually uneconomic, needing government subsidies. Geothermal has enormous potential, low operating costs, zero carbon footprint, and unlike wind and solar, it has 100% capacity factors on all. It can be on all the time, 75, 85, 100% even. However, at the moment, it's been limited to hot areas, mainly near volcanoes and geologic rift zones. And it's subject to a number of things that are problematic for the oil and gas sector, which is high capex and high upfront costs and subsurface risk. It has the same kind of subsurface risk as oil and gas does. So because of that, it's only made a small contribution to the global energy mix. It could be much larger if costs came down and if technology improves. Hydroelectric, again, not much growth expected here. Very high capex, environmental issues to do with flooding huge areas of landscape, long lead times, and so on. Biofuels and bioenergy used to be fashionable, but now they're going out of favor because they compete with agriculture for land. They cause deforestation and soil erosion and amongst other things. Wind has been a rapid growth area, especially in UK, offshore UK. Zero carbon, and very economic in today's energy prices. Offshore, it doesn't have any environmental or social problems because it's out of sight of land. However, it does have intermittency problems, 40% capacity factor. In other words, for 60% of the time, it's not delivering electricity. And that needs to be filled by other sources of energy, which typically would be natural gas at this stage. Solar works obviously best in hot and sunny locations like North Africa would be a very good place for solar. And the downsides are it takes up a lot of land area, which competes with agriculture. And it's intermittent with a 20% capacity factor. In other words, 80% of the time it's not on, which means backing it up with other sources of energy, typically natural gas again. So let's look at the carbon footprint situation here, comparing natural gas, wind, solar, and geothermal. Natural gas is a low carbon footprint. The top right picture shows a natural gas power generation plant supplying 100 megawatts. It's quite a small area. And gas is collected from a wider area underneath the plant, but the surface impact is quite small. Wind, on the other hand, is much worse. You can see from the bottom left picture, it's 5 times worse than natural gas, 100 acres for 100 megawatts. So quite a big surface impact per megawatt. Solar even worse than that, 500 acres to produce 100 megawatts. And you can see on the right bottom picture there, an idea of how a large array of solar cells would look on an agricultural landscape. Here's a slide showing the continuing drop in what's called levelized cost of energy. LCOE, different kinds of energy. If you look at the left-hand scale, it's LCOE in dollars per megawatt hour, and the bottom scale is years. If you look at onshore wind, for example, dark blue line, it's dropped in half in the last 20 years, but really the last 15 years. Offshore wind, again, has dropped significantly since about 2012, so 10 years ago. And it's more or less than half what it was. So again, becoming very economic. Solar power has been even more dramatic. The yellow curves there, dropping from 350 LCOE down to 50. That's 1/7 what it was. There's two kinds of PV shown here. PV is photovoltaic cells. Without tracking, which means that they're on a fixed angle to the sun, and with tracking means they follow the sun automatically on a clock. And that will be probably where the future is. On the top curve, interesting one, this one, that shows the cost of battery storage for a 4-hour supply. In other words, when the sun goes down, you need something to replace the solar power. If it's going to be green, then you'd really want to replace it with something produced with green energy and then store it in batteries. So that is a huge cost. It's come down from 800 down to about 190, but it's still double or treble the cost of solar or wind power. So you can't store that much without it becoming prohibitively expensive. That's a major problem for solar power and wind power, battery storage. You can store also in hydroelectric schemes where you pump water up to the reservoir and then it comes down again at night when the demand and supply situation makes it more attractive to use it. And it comes up again during the next day. But it's more expensive than solar than battery power. So how does wind energy and solar energy compete? I've covered the capacity factors a little bit already, but if you look at the top right curve there, that's the curve for the US for the last 10 years or so, month by month, showing the capacity factors for different kinds of power. And if you look at the green curve, for example, it drops every year during the winter months. So going down this list of bullet points, pumped hydro is about capex of $300 per kilowatt hour. That's a very high capex, and that's why there's not many of these plants around. They are extremely uneconomic to operate. Battery storage is also expensive. $145 dollars per kilowatt hour. That's half what the hydro cost is. Battery costs could come down in half. So if it does, then that'll become competitive. But maybe 10 years or more from now. So wind energy total growth has been over 20% per year, mainly because costs have fallen substantially since 1980. Wind turbines are now up to 20 megawatts each, with a 250 meter rotor diameter. It's enough to supply wind energy for 25,000 homes as long as the wind is blowing. The Eiffel Tower, by comparison, is 300 meters high. So these larger wind turbines are now nearly the height of the Eiffel Tower, and very shortly will be bigger than the Eiffel Tower. It's colossal. That really improves the economics hugely. Offshore is better than onshore because the wind tends to be stronger and more steady, and also there are less environmental objections. One of the interesting ones is floating wind energy offshore, because that takes you further offshore again, away from land, away from environmental objections. And it's just beginning to happen now. It probably will be the main source of wind energy in years to come. Here's an example of an installed capacity of 25 megawatts. It's the world's first semi-submersible floating wind farm. There's 3 platforms, each capable of 8.5 megawatts, which is the largest ever installed on a floating platform. And the mooring technology allows for installation in waters over 100 meters deep. Here's a diagram showing different kinds of offshore configurations for floating wind energy. Barge, semi-submersible, spar, or tension leg, which is basically derived from the oil and gas industry. They're the same kinds of things which are used in deep water offshore now for oil and gas. The one that I think will be the most prevalent will be semi-submersible, the one second from the left. And we already have one in operation, with many more in process. Here's a map of the UK showing installed capacity, with the red dots showing the onshore locations of wind farms, and the bigger dots up to about 200, 300 megawatts capacity. So big farms, lots of them. I think people haven't realized how rapidly the UK has latched onto the wind story here. And offshore, the licensed areas are shown in blue, where future wind farms are in development. North Sea is the biggest area for this. The water is relatively shallow, the wind is very strong, and you can power an enormous amount of UK requirements from these plans here. Here's a slide number 38 showing solar power potential. The sun, for example, provides 12,000 times more energy every day to the Earth than the whole of mankind currently uses from all sorts of energy. That's from Horton, who is a very notable author, ex-Met Office. So the potential is huge. I mean, if you imagine big solar farms in North Africa, in the desert, in the Sahara Desert, supplying Europe through subsea cables and so on, that's a very big, potentially very big operation. How does hydrogen fit into all this? You hear a lot about hydrogen, so what's the story here? First of all, it's a clean fuel. Emissions are only water vapor, as it combines hydrogen and oxygen to make steam. You can replace methane for a lot of applications, such as power generation, vehicle fuel, heating, residential use of heat. Challenges are very high costs, and it's uneconomic compared to the alternatives. So it's a nice story, but very expensive. And if it was a free market economy, nobody would buy it. It's being pushed by the climate agenda, and it'd have to be subsidized by governments. It's also expensive to store and transport, and it can only be used as short range for vehicle fuel, good for buses, for example, but not long range. It's just too energy inefficient per unit of weight or unit of volume. Hydrogen, there's 3 different types. They're called blue and gray and green. I'll run through a summary of what each one is just now. Blue is made by reforming with steam. It's called a steam methane reformation process, SMR. It's a low-cost operation, $3 per kilogram, plus the cost of natural gas, which today is very high in Europe, less high in the United States, but that's a factor. It needs access to low-priced natural gas to be viable. The main byproduct is CO2, which obviously cannot be allowed to go to the atmosphere, otherwise you gain nothing. If you convert natural gas into hydrogen and it all goes into the atmosphere as CO2, then you achieve nothing. So the CO2 has to be captured, and that will be done via a CCUS project. Grey hydrogen is the same as blue hydrogen, but without the CCS, so it has limited application. Green hydrogen is the one that achieves all the objectives, and it's the one that is most targeted when you talk about hydrogen projects. Made from electrolysis using green power, let's say solar power or wind power, for example, but it's expensive at $8 per kilogram. There's a proposal for 60 gigawatts to be developed worldwide. the economics are extremely, extremely difficult, so unlikely to happen. There's some more points about hydrogen here. It can be piped and it can be transported in containers, say by ship, at 200 bars pressure and 3,000 psi. But the energy intensity, the next bullet, is quite a big problem. 1 liter of petrol has the same energy intensity as 18 liters of high pressure hydrogen. So you need a lot of hydrogen to get it in any kind of distance. And then it becomes impossible because the vessels for storing it is too big, too expensive, too heavy, and so on. At the moment, 75% of hydrogen produced in 2019 is grey hydrogen. That has limited future. The future will either be blue or green, or we live with the emission problem that you have with grey. For example, there are 500 hydrogen buses operating in Europe at the moment. They have a different objective, not to reduce GHGs, but to reduce pollution in cities. So that's an example where they're working. They are used in fuel cells. Hydrogen is used in fuel cells with oxygen to generate power for small-scale applications. That's, for instance, what they used in the Apollo program to go to the moon. The EU has committed to developing 40 gigawatts of electrolyzers to make green hydrogen, which is a very ambitious target. And in today's economic environment, especially exacerbated by the Ukrainian war, that's politically desirable, but very expensive. Another burden on governments which are already stretched post-COVID and or during Ukraine's war. Cost of production, $18 per MMBTU. It's now rising to $60 per MMBTU for green, which is 4 times the price of blue. So green is nice to have, but impossibly expensive. Blue hits the target, but also expensive. Grey is almost a natural process, burning natural gas, for example. It doesn't achieve any GHG objectives. Now, you've probably heard about geothermal. This is an interesting one. What is the potential of geothermal? I'll summarize here. Here's a diagram of what it looks like. Usually, current geothermal is usually produced from hot rocks, which are say down to 300 degrees C at depth. And that typically is close to volcanoes or extinct volcanoes and in rift valley sections of geology around the world. So wherever you have rift valleys, you tend to get deep, hot rocks. And they're ideal for geothermal. And the geothermal wells are drilled on top of these. Sometimes you can inject water, as shown in the blue line there, and produce water coming up in the red line with steam as well. Most of these projects are used for power plants. Sometimes they use what's called a Rankine cycle, or a low boiling point liquid cycle, which means that you don't actually connect the reservoir steam and water to the surface facilities. You have a separate loop for them. And around the world, there's some big hot areas like Iceland, Italy, Turkey, Indonesia, Philippines, Kenya. But a lot of the world, it's not hot enough and doesn't work. So the potential at the moment is only for the hot areas, which is a small fraction of the world's surface. Interesting one for the future is what's called EGS, Advanced Geothermal System, which is rather like those who are familiar with oil and gas in Canada called a SAGD system, where you have a couple of wells, injection well and a producer well, often horizontal, and then the horizontal ones are laid next to each other. So you heat the rock through the process of conduction, which means the rock doesn't have to have permeability to make it work. And these are now in the trial stage. There's several of them in operation. And this is where quite a lot of potential is there for the future, because you don't have that very hot rocks. you can get more production out of horizontal wells. And large areas of the world are likely to open up to EDSs. However, it suffers from the same kind of subsurface challenges that oil and gas have, so that affects the economics quite a bit. Now, I'll go through some advantages of geothermal compared with surface footprint and cost of energy. If you look at the green box at the top there, the energy source for geothermal, natural gas, wind, and solar is compared. Percentage availability, geothermal, 85, can be 100%, on all the time or on whenever a base load is needed. It can spike up to deal with peak load as well. Natural gas, similar. Wind, 40% as mentioned before. Solar, 20% as mentioned before. Competitive cost of energy is good for geothermal compared with hydro, wind, and solar. And so what we have is, in the bullet points on the left, a little summary situation. Because it's an intermittency problem with wind and solar, it can be filled with other types of energy, such as hydro, but that has its problems, as mentioned previously. Nuclear is another one, again with problems as mentioned previously. The geothermal basically has none of the problems that these other sources of energy have. It's zero carbon, it's zero GHG or very low, available 24/7 to 100% capacity. Plus it has a low surface footprint, 1/5 the area of wind or 1/20 the area of solar, and the economics are competitive. So it's just a question of making it more efficient and more applicable in wider areas around the world. This is where oil and gas professionals can see some comfort, because geothermal needs almost the same skills as oil and gas. So if you're a geologist, for example, or a reservoir engineer, you can use your skills in geothermal. And a lot of geothermal companies are now starting up using oil and gas professionals as their core team. And I'm chairman of one of those companies. It's called Frontier Geothermal, and we're building the team with oil and gas expertise. It's quite easy to switch over to an understanding of geothermal, because the fact that the engineering and other processes are similar. And there's a lot of oil and gas expertise which could actually make geothermal more competitive too, such as cheaper wells, horizontal sections, and so on. Here's how it's used. If you look at the box on the right, up to 350 degrees centigrade is suitable for what's called flash steam and dry steam power for electric power generation. What I mentioned before, which is called the binary loop or the Rankine loop, is for cooler geothermal product, which you might transfer into a loop, which could be LPG, for example, which boils off at a lower temperature than water. So you can have two separate processes there. As geothermal temperatures drop in the area that you're looking at gets wider and more typical of normal final conditions, industrial heating becomes a good market, 65 to 150 degrees temperature. Building heating also is good for these areas, and in Western Europe, for example, in Germany, geothermal is used quite a lot for building and industrial heating. And geothermal heat pumps, which use electricity to make heat very efficiently using the ground as a heat sink, are suitable for normal geothermal gradients, such as UK, where you can install one of these things into your garden and it makes cheaper electricity than if you buy the electricity. It makes cheaper heat than if you buy the heat off the grid through electricity. So what's happening with the natural gas bridge? First of all, natural gas is the cleanest of the major fuel supplies of the fossil fuels. 50% of the carbon footprint of coal, 65% of oil. It's also cleaner with respect to impurities and polluting chemicals. In other words, things which are in addition to GHGs. It's got a a good surface footprint, as mentioned before. And it has a vital role in bridging fuel, while the world increases the use of green fuels. It's well suited to baseload power, in other words, the power you need to get through a 24-hour average. And it can also be used for peak power, which typically would be, say, early evening when people finish work and get home. And natural gas is available to supply power for these peaks as well. It's got a low LCOE, so it's economic. If you look at the alternatives, green electricity could cost 4 times the price of gas-powered electricity. So electricity is already expensive. Imagine what would happen if its price were 4 times higher. Either the government would have to step in and subsidize, or we'd pay much higher electricity bills. So to replace Europe's oil and gas consumption with hydrogen, we'd need many large nuclear power stations and thousands of megawatts of 10 megawatt electrolyzers to make green hydrogen, and hundreds of 1 gigawatt steam reformers to make blue hydrogen. So it's an enormous project, unlikely to happen on that scale. We're back again to what do you do as an alternate? Well, the alternate is obviously fossil fuels, but we're trying to phase those out. So not an easy solution. Here's a summary of what's happening in the UK. First of all, the UK is the 5th largest economy in the world, GDP of 2.3 trillion pounds per year. And what's happening in the UK is that growth of renewables, mainly wind, has been very dramatic. And so there's been an improvement in the overall level of GHG emissions from the UK. And North Sea oil production, gas production has been dropping, so that's another factor requiring replacement. Again, intensely mostly offshore wind turbines now. And for example, in the first half of 2020, a couple of years ago, renewables supplied 46% of UK power, mostly wind power. It's a pretty notable achievement. And it's also been caused by the phase out of coal and the replacement of oil with gas. So the final point here is much of the UK oil and gas workforce will be redeployed into offshore wind and other renewables projects. The skill sets are similar. There's great business opportunity for people who want to make the switch. And CCS injection into oil fields under EOR needs similar wells, facilities, subsurface technology, and reservoir management. So again, skill set transfer is ideal from oil and gas into these types of CCS projects. The UK has a great opportunity to lead and export technologies associated with low carbon energy and offshore wind farms. An example of this is oil and gas. Before the North Sea, the British contribution to the global oil and gas scene was not that big. We had majors like Shell and BP, but the expertise was mostly in the US. So the service companies and so on, like Halliburton, for example, were mainly in the US. With the North Sea taking off, Aberdeen became a hub for technology, both to supply the oil and gas technology and also to export it around the world. And there's a similar opportunity here for renewables, so the technology or things like subsurface, geoscience, engineering, and so on, can be transferred into these new renewable energy sectors. So here's a plot here showing annual emissions for the UK. And years along the x-axis, been dropping steadily. So if you look at the applications here, surface transport, buildings, power, and other, the surface transport and building sector has been fairly steady, but power has been dropping because new power stations are being built with natural gas rather than with coal. So there's been a big drop in emissions. And others also dropped, things like refineries and so on, getting more efficient. Here are some potential hubs for CCUS locations: Southern North Sea, Central North Sea, and East Irish Sea. And then the right-hand map shows some more locations of CCUS project locations, with the brown being the source of CO2, like refineries and industrial centers, and the blue and green circles being the storage locations, which are generally offshore. You have to pipe them from one to the other. Here's a look at what's happening with the Asian perspective. What's interesting is that if Europe and North America, let's call it the NATO countries, all cut back their emissions to zero, then globally emissions are still going up unless Asia does the same. So Asia at the moment accounts for more than 50% of energy demand growth. And that will go up as population goes up. So if there's limited reduction in GHGs from Asia and a lot of reduction from the North Atlantic countries, USA, Canada, Western Europe, we still have a global problem. Asian governments are focused on local, not global environmental issues. So European countries are saying, hey, we've got a global problem with GHGs, so let's all work together and solve it. The Asian governments are not so focused on global issues. They're more concerned on local issues, which affect democracies and so on, because cost of energy becomes a voters' problem, and access to reliable energy becomes a voters' problem. So the Asian countries should look at things like local air pollution in countries, cities like New Delhi, for example, which has a major pollution problem. A lot of the Chinese cities have major air pollution problems. Asian governments want to make electricity more accessible to more people, which means low-cost electricity, which tends to mean fossil fuels. That's usually the lowest cost. Asian governments are also pursuing clean coal, which is generally clean of damaging pollutants, but it's not clean of CO2. It still has high CO2. So when it's clean, it's not zero CO2. In China, coal will contribute about 33% of the energy mix until 2050. And in India, 40%, even higher. So those are huge numbers. It's very difficult to achieve global objectives unless these countries commit to GHG reduction in the same way that European countries have, for example. There's also a view with a lot of undeveloped countries in the world that the developed countries cause the GHG buildup and climate problems, and thus has responsibility for cleaning them up. It's quite a good argument. I can't complain with that. Then again, it means that they don't feel so morally committed to the GHG story. So what are the opportunities? This is where we wrap up here. For your companies, and then for your, here's your next page, your careers, companies first. One of the benefits is to become a world leader in energy efficiency technology, able to support these services. So the UK, for example, is becoming a world leader, especially things like wind energy. Energy companies have opportunities to invest in an operation of renewable energy. More and more of the majors are making energy commitments in renewables, especially wind and solar, especially wind, and trying to cut back on the fossil fuels. Financial benefits from gains in GHG reductions, better green image, and sale of emissions quotas, as mentioned before. Financial services can obtain benefits from providing emissions trading platforms, hedging and derivatives, a whole new arena to get involved with. Consultancies will be looking at emissions management, legal, technical, commercial services, independent reporting services, growth of renewable fuel and low carbon technologies. As far as careers go, there'll be growing demand for technical and commercial skills, as I'll show in the next slide. And in applying these skills from oil and gas into renewable sector. So this is the last slide here. If you look at the profession and the white collar, geoscientist, petroleum engineer, facilities engineer, economist, lawyer, operations manager, HSC, ESG, HR, national and public relations. That sort of makes up an oil company, those skill sets. Then you look at which ones need those skills. Energy efficiency, in other words, cutting energy in half usage, let's say, target half of what it is now. Natural gas bridge, you need ongoing natural gas operations for the next few decades. Wind power, solar power, hydrogen, biofuels, geothermal, and CCS. So which of these applications need which of these professions? The answer is the green boxes there, the X in the box. Almost all the professions are needed in almost all of these new green renewable technologies. The exceptions where they're not needed are petroleum engineer, which is not needed for wind and solar. That's more of a surface operation. And geoscientists, again, not much need for geoscientists in things like wind, solar, and hydrogen, but there is a need for geoscientists in natural gas bridge, geothermal, and CCS, because they're all subsurface operations. So being a geologist now is more challenging than being an engineer, being a lawyer, or an operations manager or facilities engineer. There's lots of potential with the new technologies. So that concludes my talk, ladies and gentlemen. Thank you very much. If you didn't fall asleep, I'm here to help with questions. Over to you, Anastasis, for that.
Yeah, thanks, Peter. We do have a few questions, and I've just scrolled up to the earlier ones, and the first one I've gone back to is by Lachlan James. I'm not sure if we can answer this question here, but it's to meet net zero by 2050. How much PV, wind, battery, storage, and/or other renewables, I guess, does the world need? And how does that translate into mineral resources required in terms of tons of aluminium, lithium, nickel, silver, etc.?
It's a very
yeah.
So carry on.
Yeah, and how does that compare to the global reserves of those materials?
That's a very good question. I think it's hard to answer all that in one go. But if you drop me an email, I'll see if I can answer some of them by email. But briefly, you've hit on a huge problem, which has not really become apparent until people started looking at it recently.
Yeah,
I've seen a lot of
arguments on LinkedIn about that. Sorry, Peter.
Yeah, sure. If you wanted to, let's say, increase a renewable fuel by 100-fold to make it able to supply the majority of energy around the world, then you've got to increase the supply of things like lithium. For instance, if you look at electric vehicles that need lithium for the batteries, electric vehicles currently make up about 2% of the vehicle fleet worldwide, so it's very small. They're anticipated to go up to most of the vehicle fleet within the next 20, 30 years. So that's a huge growth. I mean, that's 10 times, at least more than 10 times growth. Then the problem switches to how much lithium is there, and is there enough to supply this at economic levels? And people are raising their hands saying, now we've shifted the problem from GHGs to running the world out of precious metals and so on, which are needed for these other kinds of technologies. So it's a very good question, and I'm not sure there's an easy answer to it.
I think what tends to happen in those situations is that we, like with oil many years ago, we were always going to run out. And as soon as the price goes up, we seem to find more. So, I mean, I don't know what the resources are like for these metals, but I think as the price goes up, people will be looking harder and harder for them. Okay, to the next question. So Paul Rankin's brought up, the greatest energy shortage now and in the future is political will, isn't it? The question. And he's probably right, and the will to adopt policy, the will to finance and to implement in the necessary timescale is where we really struggle. And it's really evident in Australia because our Prime Minister a year or two ago was holding a lump of coal in his hand saying, why are we scared of this? And it's all about jobs and them keeping their job, unfortunately. And we're at the other end of the scale in Australia, I think. I don't know if you've got any comments to that, Peter.
I think that's right. I think what's very apparent to me is there is a lot of ambition here. To win votes, governments in the Western world and in developed countries need to show that they are trying to solve this problem. But there's an even bigger problem, which is shortage of energy supply, which we're seeing now. And that tends to take priority when looking at energy planning. Most governments and most companies in the energy sector are saying reliable, affordable energy is more important than low GHG energy. And if you look at, for instance, in France, there's been objections and riots and things about fuel price. That's been happening in other countries in the world recently as well. There you see riots and demonstrations against fossil fuels. So the political will is there, to try and get these problems solved, to replace fossil fuels with renewables. But the cost is high. The economies have to be strong to get government support to do these things. There's pressure to diversify energy sources, with, again, the Ukraine war amplifying the need for this, so that we're less dependent on single sources of energy. In the past, it used to be Western countries wanted to be independent of Arab oil embargoes. Now it's shifted to Russia. So to solve the Russia problem, we have to find 5 million barrels a day of oil and oil equivalent from around the world, so that Russian exports are not needed, whether they're stopped by embargo or sanction or just market forces or political pressure. There is this pressure to go for more diversified locations. So UK is a good example, where a big chunk of UK electric power is supplied by UK-owned offshore areas. That's a very good story. The political will is there, but it's tempered by the economic situation. Governments do not really want to subsidize things, because the world economy has been hit hard twice. Once with the virus, with COVID-19, and more recently with the Ukraine war. The Ukraine war situation is probably going to get worse. The economies of countries affected by this are going to get worse, because it's now caused an oil price hike worldwide. So all countries that use oil are paying more for their energy. And this has become more of a topic, which is how do we solve this problem before we solve the climate change problem. In the ideal world, is to solve the climate change problem by supplying renewables, so you're not dependent on fossil fuel.
Yeah.
You've got to have the money to do that, and the economies have to be strong to do that, and that's not the case today. The political will is kind of there as long as everything else falls into place. If it's difficult, and if you look at, for instance, voter opinion polls, quite often show that in the top 5 topics for voters, energy security and energy price is quite often in the top 5, whereas climate change is usually somewhere in the 10th or 15th level. So climate change is nice to have, but if the world is short of energy, then it becomes very expensive and very hard to finance.
Okay. The next comment was talking about hydrogen. One, Kabolas asked this question. How much energy to generate hydrogen out of water, electrolysis, or from methane? And I answered the question. I said about 30%, and it's around 30 to 35%. So there is huge inefficiency in converting renewables to hydrogen, and that's where, for me, hydrogen comes unstuck. I don't know if you've got any comments to that, Peter.
Yeah, I think for hydrogen to work from a GHG point of view, it really should be green hydrogen or blue hydrogen with CCUS. Yeah,
I still think that that 35% of energy can be stored, as opposed to wasted in the I don't know if wasted is the right word, but lost in the electrolysis process.
Yeah, well, it could be. I think what we're looking at here is that a blue hydrogen project is probably double the cost per unit of energy of a natural gas project.
Yeah.
And green hydrogen is about 4 times the cost. So the whole cost bit is a big problem. Plus, green hydrogen is to be truly green, can only be produced by renewable electricity, which is has the intermittency problem. So then you got a storage problem for electricity. How do you keep it all going when it's not, when the sun's out and when the wind doesn't blow?
Peter asked the question, I think we've covered this to some extent, but perhaps we'll get all the questions and write responses to them and summarize them. But it was about energy storage is surely a big opportunity, which it is, in terms of wind to battery and also wind to hydrogen. So I feel we've covered that, but I think we'll maybe summarize the answers and send them out in an email, Peter, if you're okay with that.
That's fine, yeah.
Yep. A couple of comments. Lachlan James said, 1 acre per megawatt of wind rated capacity. He thinks that seems pretty optimistic. And maybe it is, I don't know. I'm not that up to speed with the capacities of wind.
Well, the bigger turbines at the moment produce about 25 megawatts per turbine.
Yeah.
So to produce,
you're achieving that with bigger turbines, I guess.
Yeah. To produce 100 megawatts, would need 4 wind turbines. To produce gigawatt, would need 40 wind turbines.
Yeah. And Peter Lord also touched on molten salt being a potential for storage, thermal storage, where it's melted during the night with cheap off-peak electricity, and it can heat hot water during the day. So that's another option that it doesn't get mentioned very often. I remember them talking about using it for nuclear power storage.
And also, there's a solar technology which is somewhat gone out of fashion recently, but it was some projects built a few years ago, which take concentrated solar energy in the form of mirrors. They concentrate the solar energy. There's one in Spain, I think, for example.
Yep.
Uses this mirror system to concentrate solar energy on a salt accumulation or salt storage vessel at the top of a tower. And that salt storage stays hot during the nighttime and can be used to make electricity out of steam.
Right.
So another good project, but again, non-economic in today's climate. So that's the biggest problem all the time, not non-economic.
Yeah, we're not willing to put our money where our mouth is. Energy efficiency, Bernard Horning mentioned this, energy efficiency must be the first renewable and we must consume less energy. And that goes without saying. Unfortunately, we don't want to sacrifice our conveniences to become more efficient and consume less energy as modern humans. I think that's one of the biggest issues we face, is adjusting the way we live.
So Richard Branson was on the television the other night, a couple of nights ago, with his thoughts on how we should react to the Ukraine war situation. And he'd obviously been given some quite good advice by good experts. One of the points he made was that you could say, let's say Germany, for example, Germany is dependent on Russian oil. They can save a huge amount of oil consumption just by driving 10 miles an hour slower. So instead of driving at 70 miles an hour, or equivalent in kilometers an hour, drive at 60, then you save almost half your energy is saved in terms of the cost of a vehicle. The driving more slowly is one solution to the energy crisis. But do people want to do it? No, they'll have to do it if it's forced on them by law. There's speed signs saying 60 or 50 everywhere, as it used to be in the US after the Arab oil embargo, when there was shortage of oil from Arab Middle East countries into the United States. Yeah. And so you guys say with a 55 mph speed limit across the country, which was there for years and years, and it cut fuel consumption by a huge amount relative to 70 miles an hour. Yeah,
the oil crisis, the energy crisis, was a great catalyst for energy efficiency improvements. Bernard Horning made another comment, and I'm happy to bring it up, that they've recently won a Queen's Award for development of their Porter scanner, Airtight 520, to detect, locate and quantify air leaks in buildings and enable passive house building and retrofitting to pass pressure tests first time and every time, with energy savings up to 90% in some of the passive house buildings they've done, which is quite amazing.
Yeah, good example.
Well done, Bernard.
Thank you very much, Anastasis. It was announced on the Queen's birthday last Thursday, on the 21st of April.
Yep, congratulations.
But thank you. We were one of the 225 winners, and our category, we won on the it was in innovation and export, and above all, bringing something new to the market and something which had never been done, achieving a world first. And happy to contribute and help people reduce their energy consumption. Thank you.
No, that's great. It is energy efficiency and just not wasting energy. It's just, you know, I'm always in awe, not in awe, but just shocked that you walk down the high street and all the cafes have their heaters going, they close, and you go there in the morning and the heaters have been all night. They've got these gas-fired heaters running, and just little things like that, you know, they're just incredible. Sorry, I don't want to get in the soapbox now. That's pretty much it for the questions. I think what I'll do with Peter is put them in a document and issue them with, you know, some more detailed responses, as long as Peter's happy to do that. And we'll email them out to everyone. And we'll also have the presentation up on YouTube soon, within a day or so. Somebody asked about the slides. We don't give the slides out in the webinars, so but you can access them through the YouTube presentation. So if there are not any more questions, I'd like to thank Peter and you all for attending and for the good answers, good questions. Sorry. Hopefully the answers were good.